Okay, so section 1.10 to 1.13 is going to explore continuity and one-sided limits. So, in just normal talking to you, if we said something was continuous, we would say, okay, there's no holes, there's no jumps, there's no gaps. So if we took our pencil, we would be able to draw the function without picking it up at all. Now, here are 3 examples of functions that are not continuous. So number 1, if our function value is not defined. So I like to take a graph. So if I have a function value not defined, it means that I have to have one x value, which we let be c, that doesn't have an actual value. So we can have a hole. That's just one scenario. Number 2, my limit does not exist. So in order for my limit to not exist, it means the left and the right-handed limits can't be the same. So we can have the right and we can have the left, and that's still our c. Okay? And number 3 says that we have a limit value, we have a function value, but they're not the same. So I'm going to take care of this part. So if we have a limit value, it means they need to meet up. I don't have to be defined at that point. And now the second part says I have to also have a function value, but that can't be the same as my limit. So that would be my limit value. So I need to make my function value off. Okay? All right, so now mathematically, we need to define what continuity is, not just using our word definition, okay? So a function is continuous if 3 conditions are met. So look, up here, that wasn't continuous, so we need to make sure that does happen. So we need f of c is defined, which means it exists, okay? All right, the second condition is going to be kind of here. So we need our limit to actually exist. So the limit as x approaches c of our function, it does exist. And then if we have a function value and a limited value, in order for the graph to be continuous, we need those to be equal. So we are going to say, that the limit as x approaches c of our function is the same as our function value. Okay? So continuity, just by definition, is always going to be continuous on an open interval. So we're going to use parentheses. We don't need to include the endpoints. Okay? So state whether the function is continuous. I'm going to leave my definitions up there. So if any of these 3 things fail to occur, then we would know that our function is not continuous. So I think if I'm given the function 1 over x, I might not know what that graph is, but are there any values that don't exist? And remember, that's when your denominator is equals 0. So if you set your denominator equal to 0, we know that we can't have that. So then we're going to say no. And you can say like number 1 fails, or f of 0 does not exist, if you want to use some math notation. However you want to say that, okay? All right, number 2 is a piecewise function. So we have a line, which is continuous. We have a parabola that is continuous. And what we want to know is, do they meet up? So I want to look at what their y values are. So if I have the y value, x value 0, well, 0 plus 1. And even though this isn't defined, remember that would have been an open hole. I want to make sure that that is getting filled in by the top. So if I plug in 0, 0 squared plus 1, and so they both have the same point. So I know they're going to meet up. I'm going to have a line, and then I'm going to have a parabola. Okay, and you don't have to graph this, but we're going to say yes, for it's continuous for all real numbers. Okay, my last one. Now, this is a rational function, so we're always concerned when our denominator is equal to 0. So if I solve this, I know x equals 1, and that's the value I can't have. Okay, now what happens though is I know that this numerator factors. So let's say we just didn't set our denominator equal to 0. So if we factor the numerator, and we leave the denominator alone, these terms would reduce. What's left, that gives you the shape of the graph, okay? But when we're talking about continuity, it always goes back to the original function, and we cannot have x equals 1. So we're going to say no, x cannot equal 1. All right? So if a function is not continuous, then we call it discontinuous. We don't call it uncontinuous or not continuous. It's discontinuous. So there are two types, removable and non-removable. So I like to think of removable is typically when something factors and reduces, because that's going to produce just one whole that if I would plug it, then that's why it's called removable. I can just take that one little value out. Non-removable is usually when you have asymptotes. So examples of non-removable. I like to do graphs. So piecewise always work for anything, but if these are completely disjointed, I can't just put one value in to make it continuous. That's what non-removable means, okay? Also, if I have asymptotes to infinity, I'm going to make it at 0. So at x equals 0, I can't fill anything in to join those, okay? All right, removable is when we just have one little value missing. So we could do something like this, okay? And then we could also do, even if I did put a dot, okay? So you don't have to have that point off of it. Both examples make it removable. All right, and that example number 3 up here, oops, number 3 up here, this, because that factored and reduced, that would be a removable example. So one-sided limits. Instead of looking at both directions, we can look from only one direction. And so you need to understand the notation. So when you just had the limit as x approaches c, you had to look from both sides to see if they met up, okay? And that's really a double-sided limit. We just don't call it that, okay? So now there's right hand and left hand. So the notation right here, you're going to notice there's your target value of c, and then there's going to be a little plus. So that's called the right, or I like to call it the upper, because you're looking at the graph from the right. Down here, if you see your c value and there's a little minus, it doesn't mean negative. That means left, or you can think of it as lower, okay? So let's look. What makes one-sided limits special is this. One-sided limits can have a value, where double-sided limits or normal limits does not exist. Very rarely will you have a one-sided limit that does not exist. Like I can't even think of one, okay? So let's look at number 1. So this says that 3 is our target. So what you should do is I like to just make my eye go right to that 3. And this little negative says what's the y value that we're approaching as you get closer and closer to x equals 3 from below or from the left. So you want to go to the left of your graph and you want to follow the graph, okay? And as we get close to 3, well, it's going to also equal it, but remember that doesn't matter. Our y value is getting close to 1. All right? Then we're going to do this one. So our target is still 3, so we'll still be looking here. And we want to approach 3 from above, so 3 from the right. So I go to the right and I follow that function. And we say, well, I know I'm not equal, but all my y values are getting closer to 4. Now, for my double-sided limit, or just my limit as x approaches 3, you have to check both sides and see if they agree. Well, they aren't the same number, so that's when does not exist. We can't have more than one answer, so that's also your clue. Part D says f of 3. So that says, hey, when x equals 3, what's y equal to? So we go to our graph and we see the filled in dot. All right. So you want to really be familiar with all 4 different notations. And it's asking us 4 questions without using any words. All right? So let's look at part A. So now, one-sided limits are also kind of the same as double-sided limits if they exist. It won't matter. So if I just want to try 2, as long as when I plug in 2, that's going to be the same from the left or the right. So substitution is still your first strategy. So if I plug in 2, we get 6 over 6, which does exist. So my one-sided limits and my double-sided limit, they're all going to be 1. Look at part D. Now if I plug in 3, I get 3 minus 3 is 0. And 3 squared minus 9 is also 0. But 0 over 0, that's not equal to 1. It's not equal to 0. It says, hey, remember, there's so much math here you need to do first before you can plug me in. So we're going to factor. These are perfect squares. So once I reduce, then I can go back, and we still have our limit here because we have not evaluated it, and I get 1 over x plus 3. Then I can try substitution. If we plug in just regular 3, it's not undefined, so it's going to be 1 over 6. Okay, and for the last one, we've got x minus 1 over x squared. So if I plug in 0, we're undefined. So remember, if I have a really small number over something that's bigger, our choices are going to be infinities. So we really just want to test, is this going to be positive infinity, negative infinity, or since we only have one-sided limit, it's only got to be 1. So I want to plug in, since it's from above, I want to plug in a positive decimal. And just find out if we're positive or negative, okay? Because remember, infinities are your choices. So if I plug in 0.01, I would get a negative number on top, and anything squared is going to be a positive. And so a negative over a positive is going to be negative infinity. All right. So the existence of a limit. This is just by definition, and you need to know these ideas and how to kind of read the math. So let f be a function and let c and L be real numbers. The limit of a function as x approaches c is L if and only if we've got the limit as x approaches c from below of our function, and that's the same as our limit as x approaches c from above. Okay, so what that means is that our left and our right limits are equal. Okay? Now, we can use that idea to extend the definition of continuity. So a function is continuous, and this is going to be kind of the definition on a closed interval. So now we want to include the endpoints. If our limit from the right of our function is f of a. So that means, so here's f of a, it's that dot, and our limit from above, okay? And then here, limit as x approaches b from below, and that equals the function value. So then you know our endpoints exist. All right? So go ahead and give your homework a try and see how you do.